Sounding Crisis, the research project on climate change and sound.
Welcome to the Energies Consciousness lecture. It's the second meeting of our Energy Humanities Reading Group and is the first one with a wider audience and a special guest who will give a lecture to us. It is our great pleasure to have the Danish climate scientist Anders Svensson with us tonight. In a few minutes, he will present his research on Greenland ice cores and global warming to us. After around about 1 hour, we will then switch over to a discussion for approximately 30 minutes to deepen our understanding of Anders' presentation, but also to discuss the differences of the two cultures, of the way a physicist like Anders approaches the topic of energy and the approach to it by the members of our reading group who all have a background in the humanities. Just a quick remark on our approach before I'll introduce Anders and hand it over to him. We are a group so far of around about 8 people from all over the planet. Until August 2022, we are planning to meet 2 times a month. At the first meeting each month, we discuss 1 or 2 texts or a movie in the context of the emerging field of energy humanities. This relatively new area of scholarship is concerned with understanding how energies are implemented in our lives, but also how to think about and how to imagine them differently than the dominant petrol culture due to its fixation on fossil fuel does. Therefore, in the upcoming months, we will read and discuss also social, political, and anthropological aspects of energy. We will engage with indigenous concepts of it and artistic research in the field. In his influential text, Energy and the Evolution of Culture from 1943, the US-American anthropologist Leslie White stated, quote, "Everything in the universe may be described in terms of energy. Galaxies, stars, molecules, and atoms may be regarded as organizations of energy. Living organisms may be looked upon as energies that operate by means of energy derived directly or indirectly from the sun. The civilizations or cultures of mankind also may be regarded as a form of organization of energy." End of quote. What I like about it is that it links the physics of the energy of nature, to quote the title of ECPH's book we discussed at the first meeting of the group 2 weeks ago, to the cultural dimension of energies. It is this cultural side of energies which is of core interest to the energies humanities, which view energy dialectically as something that influences culture and at the same time is influenced by culture. And this leads me finally also to climate change and global warming as anthropogenic, man-made phenomena, which we are experiencing and witnessing in the current historical era of our times in ways of bushfires, melting glaciers, and rising sea levels, to name but a few, as results of more than 200 years of industrialization and globalization. Climate change is certainly also a major reason for the emergence of energy humanities. However, when discussing global warming, it seems of course wise to start with a foundational unit on climate science. Thus, it is our great pleasure to welcome Anders Svensson at our meeting tonight. Anders is Associate Professor at the Physics of Ice, Climate and Earth Research Group at the Niels Bohr Institute of the University of Copenhagen. There, he is also Head of Studies of the Climate Change Master's Program. Originally trained in atomic physics, Anders has worked on climate change for the last 25 years, specializing in ice cores, paleoclimate, and geochronology. He and his colleagues also conduct annual field research in Greenland. What exactly they are doing there and in what way it is related to climate change, that's what he will present to us now. Anders, please, the floor is yours.
You all hear me, and then I will just get my presentation up here, hopefully. I see the presentation now. Do you also see it? Yeah. Okay, super. Yeah, so thank you very much for the invitation to talk about my work and my favorite topic, ice core drilling, and what we can learn from these ice cores concerning climate change. So I'm going to start to bring you up to Greenland. And in the first slide you see here, this is actually from the center of the Greenland ice sheet. It's our camp that is located up there in the middle of nowhere, absolutely. So it's a desert, and there's 500 kilometers to the coast. And that's where we go normally every summer to drill ice cores here from the surface of the ice sheet and 3 kilometers down to the bedrock of the ice sheet, so below the ice sheet, all the way through. That's the goal. However, the last 2 summers, it has not been possible to go to Greenland because of Corona. So we have had cancellations, and now our camp has been sitting up there for 2 years with no maintenance. And that's not so good, as I will show you. So you can see things are a bit spread out here. And the reason is that it's snowing every year. And in Greenland, we have at this site about 0.5 meter of snow every year. So, and then it's blowing a lot, so there's a snow drift. And the thing is that if you put something up on the surface, the snow drift will start to fill in a lot. So that's why we have spread the buildings out. If you put them too close, they will have snow to the roof very quickly. So this slide here shows what our camp normally looks like when it's in a good shape. So in the top there, you see the main building is in the center. It's our dome. Where we're living and have a kitchen and radio and everything. And then there are smaller tents outside where people are living, quarters, and garages. And then below the snow surface, we have the ice core drilling taking place and our laboratories where we work with the ice core every day. So that's what it should look like. And below, it's just to show that outside the camp, we have this landing strip. So skiway, as we call it, where the airplanes come from the coast and bring in people and food and take out the ice cores when we have drilled them. So we're absolutely dependent on this collaboration with the US, where they have these Hercules airplanes that they have skis on and they can land on the snow. It's too high and too far to go with a helicopter, so you need these big airplanes. Yeah. Now, because of Corona, we have not been up to the camp as we normally are. So usually we would go up there in May or so and stay over summer and then go back in August. And we would have exchange of crew and ice cores and stuff every 3 weeks or so. So the plane will come in and pick up stuff and new people, and we will have an exchange. So when we go up in May, it will be might be minus 40 degrees, and then it goes up to the melting point in the middle of the summer and down to minus 40 again. And then it gets dark and it's time to leave. However, in the summer, the sun is up all the time, so plenty of light and no excuse for not working. But what has happened here the last 2 years is that the snow has been filling in. So we had people going up there just for a short visit one day to check out how things look. And this was a photo they took from the airplane, and you can already here see that there's quite some snow. And they went down on the surface and looked at conditions. And you see here in the lower left corner, you see the garage where this vehicle is normally parked inside, and you see the roof is maybe 4 or 5 meters up. And on the other picture, you see that the snow is going exactly up to the roof, because this is what happens. It's blowing around the snow and it will not stop filling up until it reaches the top of any structure you see on the surface. So our problem for this summer will be that the snowblower and the machinery we need, the generators, they will be inside this garage. We will have to dig our way into it to get stuff out and get things started. So there will be a full month of just digging snow and things like that. So we will be sure to bring some students up this year because there will be a lot of manual work. However, we are not in such a bad shape anyway, because the main building that you see here is fortunately made round, like an igloo. And there's a reason why you build things round, and that is the snow will not pile up on the sides. So you see that we still have access to this main building. It's a 3-floor building with a control tower in the top and the kitchen and dining area in the bottom. And we will actually be able to enter that and get some heat and start melting some water. So it will be okay, we think, to get up there this summer. All right. How does it work with these ice cores? Well, this is a cross-section of Greenland ice sheet. So it's about 1,000 kilometers wide and 3 kilometers high. And the idea is very simple, that every year you have this new layer of snow piling up on top of previous layers. So you get these annual layers that are nicely put on top of each other. And in the top of the ice sheet, the snow will be compressed into ice. So the half meter of snow we get every year is compressed into 20 centimeters of ice. So each annual layer will be 20 centimeters thick. However, the ice is constantly flowing. So there's a constant flow from the central parts and out towards the coast, where you have melting and icebergs breaking off and things like that. So there's a constant flow of the entire ice sheet. And as these annual layers, they sink into the deeper part of the ice, they will be thinner by stretching. You can see it illustrated there in the center of the figure, that the 20 centimeter thick annual layers, they will become thinner and thinner as they go towards the bedrock, and they will be paper thin at the bottom. So we have good time resolution, you could say, in the top of the ice sheet, thick annual layers there. And then as you go back in time, layers will be thinner and thinner towards the bedrock. The longest continuous ice core record we have from Greenland is 123,000 years. So that covers our present warm period, the Holocene, and the last glacial period, and also part of the previous warm period, the previous interglacial period. That's called the Eemian. I will show you this a bit later. However, the ice sheet is thought to have been in Greenland for several millions of years, but most of the old ice is gone because by this process here, that simply the ice, the oldest ice is compressed too much, so it's folded because the bedrock is not as flat as it is shown in this figure. So when you have flow over a bedrock, you will have a mixing of the old layers. But you also see that if you want to go far back in time, you would prefer to go up on the central part of the ice sheet, because if you go closer out to the coast, the layers you will get in your ice core from the deepest part will typically be folded, because exactly the ice has been flowing over a bedrock that is not completely flat. Yeah, but this is a principle, and this is a business that has been going on for 50 years, that people have going up to Greenland to drill these ice cores, trying to find the best places to go the furthest back in time. And 120,000 years, that's what has been possible so far. So currently we have this project going on that's called EGRIP. So there has been several deep drilling projects in Greenland, and they are shown here on the map. One was GRIP drilling, it was back in the 1990s. Then we have the NEEM drilling that's terminated 15 years ago, and now we are at this EGRIP site. And the colors of the map here, they show the surface velocity, so how fast the ice is flowing towards the ice margin. And you see that in the central part of Greenland, there's almost no flow. The flow is just downwards, and there's almost no flow towards the sides. However, as you go closer to the coast, you will start to have glaciers and a faster movement. So that's actually the purpose of this drilling here at EGRIP. You see, we are not up on the central part of Greenland as the previous drillings have been. We are going into an ice stream in order to learn about the ice flow. Because in a global warming, we want to see how is the ice sheet reacting. And that is better to study if you go to a place where there's some action and some flow of the ice, rather than being in the central part where nothing is really moving, but where it's good to find the oldest ice. So at this EGRIP drilling site, we're actually not expecting to go very far back in time, but we are hoping to learn something about the ice stream or the flow of the ice. You see there's sort of a river, ice river, right at this place. And we want to know why, and actually also how does it react to global warming. So in principle, we would like to go further out and closer to the coast to study the ice movement. But there's a limit to how close you can go to the coast, because you will start to have crevasses, holes in the ice, and then it gets dangerous to work there. You cannot land airplanes, and scientists will drop into the crevasses, which has actually happened recently to some of our colleagues, because the crevasses are coming closer up to the center as the ice is melting more. So places where it used to be very safe to be, it's no longer safe. At this site where we're drilling the ice core, it is still safe, and we can have airplanes and we can work there, no problem, no crevasses. But the location is moving 65 meters every year. So when you come back the year after with your DPS, the main dome will not be where it used to be. It will be down the ice sheet. So that's how it works. You don't feel it when you stand up there that it's moving, but it certainly is. Yeah, and just below, I'm sorry, it's in Danish, but it just gets to how it usually, what is a schedule for doing a deep drilling like this. It's something that takes in total 5-10 years. You start by applying for the funding, and then you go up and build the camp, and you start drilling. And the drilling itself will take several years because it's 3 kilometers to the bedrock, and you can drill 3 meters at a time if everything goes well. So you need to go into the borehole 1,000 times. And then things are not always going as expected. This year we had Corona, and so of course we are now delayed. And it says here that we were supposed to close our camp in 2020. So that didn't happen, and now we will have extension for, we also had all the kinds of troubles. And exactly at this site, we are really excited about how it would be to drill into the deepest part, because this is where the ice will actually be flowing over the bedrock and be deforming. So as soon as we drill, the borehole will probably be deformed, and we are afraid of losing our drill. So this will be very exciting this summer, where we will try to reach the bedrock for the first time. All right, just a few photos here showing you what it looks like. So this is in Sønderstrømfjord, the international airport of Greenland, where you go by commercial flight. And then you change to these Hercules airplanes that are run by the New York National Air Guard. So Americans have a lot of activities in Greenland, among those in Thule, where there's a big radar station. So there's a lot of activity, and actually the pilots are training to land on ice in Greenland using these airplanes. They have skis under them also, and they then use them also in Antarctica in the summer down there. So they go to Greenland in the summer in the northern hemisphere, and then Antarctica for the southern hemisphere. And here we are going into onto the ice sheet some years ago. And after some time, we will have built up this camp, where you see now it's a model of what the camp looks like. So we have the structures on the surface, and then we have these tunnels that we just use a snowblower to make a big tunnel, and we put a roof on top. Then we have a perfect freezer to work with the ice cores up there. And to the left, you see the tower with the drill sitting on it, and it's hanging in a cable. And then the drill will go down into the borehole, drill hopefully 3 meters of ice core, come up again, and then you can tilt the tower and pull out the ice core and put it together with the previous core, so you're sure you're not lost any of the past. And then we'll be standing there in the tunnels with our students and colleagues from many different countries. Actually, we have between 10 and 20 different countries participating in operations like this. And we'll do measurements on the ice core and cut it, pack it into boxes, and then fly the ice out and put it into the freezers of the nations who have paid to the project. Most of it will be stored here in Copenhagen, and we always keep the complete ice core, so you can never ask for a full ice core. You can ask for a piece of it, but we will keep a continuous record so that you can go back and get samples if you find something interesting to investigate later on. Okay, so there are these challenges of building these camps up there. This was a drill trench, so where we had the drill standing. It was 6 meters to the ceiling 5 years earlier than this picture was taken. And you see the snow is coming up on top. So the roof is coming down and the floor is coming up, and from the sides it's being squeezed. And it's not that it's dangerous to go in there. It's not collapsing. It's just being squeezed like this and going into the deep ice sheet and probably coming out at the coast in some millions of years, where some archaeologists, they can start wondering about what was going on in Greenland at the time. However, this is an old camp, and you see we used a lot of wood here to construct the roof. And that wood is impossible to get out again. I mean, you can't remove all that snow again. So we are not allowed to build camps like this anymore. We are not allowed to leave anything in the national park in Greenland. So we had to think about something to build these kind of tunnels without using this roof. And my colleague who was standing there in the yellow dress, he got this brilliant idea that, well, we don't need this wood. Let's use a snowblower, make a big tunnel, then bring up a huge balloon, blow it up full of air, and then blow snow back on top of the balloon. Then this snow that you blow on top will actually harden, and you will get a hard roof. And after a few days, you can let the air out of the balloon, and you have a nice tunnel. So that's what you see in the lower right picture there. That's a tunnel made without any wood for construction. It's just the air in the balloon that was taken out. Of course, when we did this the first time, the students were a little bit nervous about entering this tunnel, and we had to work there the full day. Is it safe to be in there? But actually, it's completely safe. It's just as good as a wood construction after just a few days. So this is how we do it now. We build these tunnels without bringing any construction material up, and also we don't have to bring it out again. Because actually, the main cost of having a project going like this is all the flight hours, all the fuel you need to burn to bring up material and bring stuff out. So we're really happy that we don't have to bring all this wood up now, and also that we can leave the environment clean after our drilling operation. Okay, that was the sidekick. This is the drilling trench. You see here we have the high roof, and the tower there is 10 meters long. The drill is sitting on it. It is also 10 meters. The ice core will come up in the bottom of the drill there and sit there. There will be, electronics and motors and stuff to control the drill. It takes 4 hours to drill 3 meters of ice core. You go down for 1 hour, you drill half an hour, you take the drill up 1 hour, and then you take the ice core out and clean the drill, and that's sort of a 4-hour routine. So we have people working there typically 16 hours a day, and the core production is just going like nonstop on a good day. Right, when the drill comes up, it looks like this, and you have here beautiful ice core sitting in the center of the drill. You see the knives that are rotating on the drill that are freeing the ice, and when the core barrel is full of 3 meters of ice, you just pull up in the drill, and there are knives that are going in and breaking off the ice core. So you get a nice new 3-meter ice core there. When you do this drilling, you produce some chips. So these cores, they're cutting out some ice chips, and it's very important to get those up with the ice core. Because if they are sitting in the bottom of the borehole, the drill will get stuck next time you go down and start drilling. So there's some transporting spiral here on the outside of the drill that will take the chips and put them up on top of the ice core. We once failed doing this, and we have an ice core drill sitting in the middle of the Greenland ice sheet since 1992. And we tried to pull for many years, but it's still sitting there. So you can lose your drill, and that's a really bad situation. You have to go back to the funding agencies and say, sorry guys, we lost it. Could you please pay for another project? And that was what we did at the time. I mean, they already spent so much money, so yeah, why not? It would be a waste to stop it, but we really tried to avoid that, and we have learned the technique how to do it. Another thing is that the borehole needs to be filled up with a drill liquid. There has to be a liquid in the hole. If you don't put anything, it will just collapse from the pressure of the ice. So we fill up the borehole with petroleum, aviation fuel actually, which is very good. It has the same density as the ice, but it doesn't freeze. So that's necessary. Otherwise, it's not possible to drill these cores. Okay, sometimes there's a reason to celebrate, and here we have our professor holding up a core from, you see, close to the bedrock. You start getting these dirty layers in there. Normally the ice is perfectly clean and transparent, but when you get close to the bedrock, you have to imagine you are you drill into a landscape that is maybe something like what we have in the Alps or so today, when the ice sheet started to form, and you will have mixing with the bedrock material. So this was the clear sign that we were getting to the bedrock, and then you know that the project is a success, and you have a good reason to celebrate. And celebration is actually something we do a lot, because you sit up there with a group of 30, 40, 50 people, and the next plane is coming in 3 weeks. So you better stay friends with these guys. You have to work with them and collaborate. So we do a lot to make a good mood in the camp. We have a cook that is normally making the food, and you don't have any worries, and we try to celebrate every occasion we can think of, and make people having a good time. You see, on Saturdays, you would normally take a shower. You don't take showers every day because you have to shovel all the snow into the snow builder, but we would do that, and we would have people cooking from their home country, you know, and have a big party. We have the best disco on the ice sheet, I can guarantee you that. So that's something we think a lot about. However, sometimes we get surprises, and this was certainly one. There has been these hams up on the ice sheet, you know, for at least 30 years, and there has never been any icebergs coming to these camps. However, the morning in the summer of 2018, somebody went outside the tent to pee, you know, around the corner, and suddenly there's a polar bear standing right in front of him. So everybody into the main dome, and unfortunately, the bear had to be shot, because it's simply too dangerous to have these animals running around. I mean, if you are at the coast, you can scare them off, and you can hope that they are not coming back. But at this site, there's nowhere else to go. As I said, 500 kilometers to the coast. It will not go away. It can smell the food and the garbage that it's looking into here. So yes, unfortunately, it had to be shot. And fortunately, we had actually a rifle in the camp, because we had not had use of it for 30 years. But it's something, you know, when you work in Greenland. So it's actually something that has happened several times now. We have had 2 visitors the last years, and the American camp also had a polar bear. So something has changed for the polar bears in Greenland for sure. We can only speculate about why it is, but certainly they are going to places where they did not used to go. All right, let's get to the science part of it. Why are we drilling these ice cores up in Greenland? Well, the reason is, of course, that we can study the past climate in a very high detail. And we really want to understand the climate system of the Earth very precisely, because we are going to try to predict what is going to happen in the future with global warming. So we want these precise records that tell us about the past climate, and then we want to use them to train climate models so they can reproduce the past climate, and then hopefully also tell us about what is happening in the future, where things will be looking quite differently from what they have been looking for actually several millions of years. What we can learn from studying the ice cores is, among others, what was the climate like in Greenland and also in Antarctica, where you can also drill ice cores. We also have these air bubbles encapsulated into the ice. When the snow is compacting into ice, we get these air bubbles in there. That means if you take a piece of the ice and you crush it, you will get this sample of atmospheric air from the past released into your instrument. So this is how we know how many greenhouse gases, how much CO2 and methane there was in the past in the atmosphere. And that's, of course, a super important knowledge to have, because this is how we can see that things are quite differently now from what they used to be. If you want to understand climate, you also need to know about past volcanism. Big volcanoes, they have a cooling effect of the Earth because of all the ash and sulfur particles they send up in the stratosphere that screen some of the sunlight. So they lead to a cooling. And when we see cooling events, we will look for if there has been a volcano in the past and how many and how big, etc. If, of course, the sun had any changes, significant changes in recent times, that would have had an immediate effect on climate, of course. We cannot measure the strength of the sun directly, but we can do it indirectly. And certainly the sun has been very stable for the time the ice covers, or the ice cores they cover. And then there's a lot of impurities, small dust particles, etc., that we can also study and learn something from. I will show you a few examples of that. Right. So if we start with the climate part, then the temperatures, we study those by measuring the composition of the water, actually. So, you know, regular water is out in the ocean and up in the rain and the clouds. And there's a special type of water, which is heavy water, which has a heavy isotope. So usual water is H2O, and the O would be a 16O. but there is heavy water also mixed up with it, where you have an 18O instead, so a heavier oxygen molecule. And it shows up that the colder it is, the less you will have of this heavy isotope in the snowfall. So measuring the amount of this heavy water, or the ratio to the normal water, in the ice itself can actually, it gives you a proxy for the past temperature. The colder it has been, the less you get of the heavy isotopes. It's simply more difficult for the heavy molecules to evaporate from the ocean when it is colder, so you get less of them in the rainwater and in the snowfall up in Greenland. So that was our former professor Willy Dansgaard there with the pipe, who figured out that just by measuring the composition of the water and the amount of heavy water in the ice, you can actually reconstruct past climates. And that's what we see an example of here in the curve there. So it's an ice core from southern Greenland, and it's a depth scale. So we are from 70 to 77 meters depth. And small samples have been cut from this ice core, and they've been measured on a mass spectrometer. That's what he's doing there in the lower corner. And it shows up that you get these wiggles as you go down through the ice sheet. And that is because the temperature has been changing. So when we are up, it has been warmer. It's summertime, and when we are low, it has been cold. It's the winter time. So you can simply see the annual layers directly from these measurements of the isotopes, just like you count tree rings in a tree. So that means you can date the ice. You can find out how old is it just by counting these ice layers from the surface and downwards. So here we are at 70 meters depth, and we are back to 1819 AD. And you just have to count how many wiggles there are, and then you get further and further back in time. And you can use this technique to count 8,000 years back in time or so, where you know each year very precisely what depth it is at. Right. So to do that, you need to cut lots of samples. And again, this is where the students get into the picture. We bring our students up every year because we have to cut an awful lot of samples. To do this, for 3 kilometers of ice, it's like 60,000 samples you have to cut. And this is Irene here. You see, highest fashion from the 80s. Some of you may remember these trousers. She's still smiling happily here because it's the beginning of the season. Maybe 5 weeks later, 20,000 samples later, she is a little bit more tired of this job, because we have parties, yes, but it's actually also a lot of routine work, and 3 kilometers of ice is a lot when it's coming every day, meter by meter like that. I don't know. We have I see there's a chat. Is it that we have some questions? Or nope. Okay, I just move on. You just stop me or ask if you have some questions. Yeah. All right. So anyway, this is the ice core is cut up simply here, like by saws, like you use for wood, and you take all these samples and you measure them back home, and you get these curves where you can then count all the annual layers back in time. And that's what the curve shows here. So we are back into 1740, 1730, etc. But of course, sometimes it's not a perfect wiggle, and you are in doubt: is it a year, or was it a short summer, or whatever? So you need to do this on several ice cores. So you repeat the exercise in several places, and then you can put the ice cores together by the volcanic layers that will be the same in all the ice cores. And by the way, the volcanoes of the historical times are also well known, so we can check if our dating is right by linking to these historical eruptions. And then, of course, as we get further back in time, we don't know what eruptions have been there. We cannot use them anymore, but we can check it up in the top part of the ice sheet. Right, so this is what it looks like in the upper part of the ice sheet. But of course, we drill the ice core all the way to bedrock, and the water isotopes, delta 18 as we call it, will actually tell us about the past climate all the way to the bottom. We will not now see the annual layers anymore, but we will see how climate changed. And that's this curve here, where we are seeing from the top of the ice sheet, that's to the left, and then all the way to the bottom, 3 kilometers down, that is to the right side. And it's again this heavy water measurements, ratio of heavy water in the ice, delta 18. Instead of seeing the annual layers that I showed you before, they are still there. Of course, they will be out far out to the left. You don't see them in this resolution. We now see how climate has changed in the past. So when it was warm and when it was cold. So it's a proxy for climate. It's not the direct temperature here, but when we are up, it has been warm, and when we are down, it has been cold. What we see clearly in these ice cores is how climate has changed over this period that is now 120,000 years. So the last 10, 11,000 years, you see, it has been warm. We are high up in the values, and it has been stable climate. So good climate for us, for developing civilizations, nice and climate, warm conditions. Before that, we have the last glaciation, so 100,000 years of cold climate, but not only cold. You see, it's not that we are down in the curve all the way. We have all these wiggles showing up. And this was thought to be, first time the ice cores came from Greenland, people thought this cannot be what climate looks like. It looks like abrupt climate change going on throughout the last glacial period. Why should that be? So it was actually thought to be a mistake or mixed layers of ice when the first ice cores came. But we now know that it looks like this. It looks like that in all the ice cores. It looks like this in marine sediment cores taken in the Atlantic, or in cave dripstones, stalagmites taken from caves in China. So the northern hemisphere really had this unstable climate during the last glacial period. Okay, so we would like to know why was that, and is that something that only happens in glacial periods, or would it also happen in a warm period, for example? Then to the very right side of the graph, we are going into the last interglacial period. So last time it was warm on Earth, all natural. And you see that the isotopic values are going a little bit higher than in our present Holocene period. So it means it was a natural warmer period than what we're experiencing today. So it's a period we're really excited about investigating, because the climate may be something similar to what we will quite soon experience here in our present time. So how were the greenhouse gases, what was the sea level, etc., in this natural warm period? That's something we like to know. Unfortunately, it's actually melting at the bedrock of the ice sheet, so the ice core stopped here, and the most exciting place, we didn't get the onset of this warm period. Okay, but let me get back to these unstable climates, these events going on through the last glacial. It's actually still not completely understood, but what we think is going on is that we have a change in the ocean currents in the Atlantic going on during this the last glacial period. So as you know, today we have the Gulf Stream bringing up warm water from the tropics to us here in North Atlantic, and giving us much warmer temperatures in the North Atlantic than we would have had without. And that Gulf Stream has been running for the entire Holocene, 11,000 years for sure. But we think that during the last glacial period, this stream was shut down, or at least much weaker, for the periods where it was very cold. Because what happens then is that you can form ice, sea ice on the North Atlantic, and then it gets just extremely cold, and this can happen very fast. So for whatever reason that we are not quite sure about, it looks like the Gulf Stream here and the ocean transport of heat and energy was shut down for periods during the last glacial, and then it was turned on all by itself. So it happened like 25 times during the last glacial period that it was turned on and off. You may know also that this is also a concern for today or the future, that if we have a lot of melting from the Greenland ice sheet, we get lots of fresh water flowing into the North Atlantic, and this may actually make the water lighter and may stop this deep water formation that drives this whole ocean circulation that is going on today. So it's something we really like to understand what was going on during the last glacial, because it may make us understand the mechanism that drives this ocean circulation, and also to estimate or to better know what is the risk of this happening in the future. Some scientists will already give you headlines that this ocean current is closing down now or very soon, getting weaker, and others will say, no, it's just changing a bit of position. The thing is, we do not have really long-term measurements of the ocean current in the Atlantic, so it's a little bit of speculation when it comes to the long time scales. But for sure, during the last glacial, it looks like something was happening there. All right, what more? Well, volcanoes, as I said, it's important to know about volcanism of the past if you want to understand climate, because of their cooling effect. And we have had volcanic eruptions in recent times. Maybe some of you remember here Eyjafjallajökull 10, 11 years ago, when we could not fly, at least in Europe, and there was a big disaster, and there was all these ash particles in the air, and so it's very disturbing. Unfortunately, this our record shows that this was just a small eruption. Over time, there has been much bigger volcanic eruptions, and we certainly don't want to experience those too often. They will come, but there's a long time period in between. But we can certainly map out what kind of volcanism have we had in the past, and we do that with a very simple setup here. As you see, we take simply a pair of electrodes with 1,000 volts between them. I'm holding them there on the ice. We drag it along the ice core. And if there's anything that can lead a current in the ice, you get a signal. And what can lead a current in a frozen ice core is H+, and H+ comes when they have sulfuric acid. So it's a simple way of measuring the amount of acidity in the ice. And this acidity comes with the volcanic eruptions. So we can detect the volcanic eruptions with this simple measurement. And the result you see here on the curve is time scale. We know the annual layers, we counted them, and then we get these spikes from time to time when there has been big eruptions. So for example, Laki eruption 1783 in Iceland was a huge disaster, and much of the animals at least died, and people got sick, and the Danes didn't come for help and all this. It was pretty bad. And it's a huge spike here because Iceland is located just next to Greenland. However, if the eruptions are big enough, the sulfate will make it all the way up in the stratosphere and be distributed all over the world. So Tambora, 1815 AD, was in Indonesia, and still it gives rise to a big spike here in Greenland. So we can really see all the big eruptions that have been in the past. And of course, as we go further back in time, we'll just not know what eruption it is, unless there is some ash particles that comes with the acid that we can analyze and then maybe find the source. And that's what you see here. And a perfect example from the last glacial period. You look at the otherwise clean ice, and suddenly you have this dirty layer, and that's ash particles, and you can analyze them, and they come together with a big acidity top here, sulfuric acid. And you see that the composition of the ash particles is just the same as what is lying next to Katla in Iceland, so the big volcano there. And so now it's known that this ash layer comes from Katla, and it came 29,000 years ago. So 1 centimeter thick is this layer here, and that's about the thickness of an annual layer at this depth in the ice. So this was a year when the Greenland ice sheet was dark because of ash from Katla. So there was a lot of ash coming. That's the kind of eruptions I don't think we can say we should try to avoid them, but we certainly don't want to experience them, because that will be just a huge disaster. All right. Other things that we measure in the ice, examples are given here. We measure everything we can, all the impurities there are. They're not so many, but and they are low concentrations, but we measure everything to learn as much as we can about the past climate. So an example here is we measure sodium. It comes from sea salt, so it tells us about storminess over the ocean. Calcium comes from mostly deserts, so it's dust that is blown from the dry areas, actually in Asia, Eastern Asia, and makes it all the way to Greenland as dust particles. The sulfate comes from the volcanoes. Ammonium is when you have forest fires, and the nitrate in the bottom there, we are not exactly sure how it's formed, but we measure it, and then we try to make an interpretation at some point. And I showed you the example of how we used to cut samples one by one, but today, fortunately, we also can measure continuously. So we simply take a stick of the ice and we put it on a hot plate, as you see there in the top of the figure, and we melt it and suck the inner part of the meltwater into this machine there shown at the bottom. It's like clockwork. It's made in Switzerland, sure enough, because everything has to be running at constant speed and the right temperatures, mixing all the chemicals, and then you can then measure all of these impurities at very high resolution, and again actually see changes in all these proxies of the past. And that's also what we use for dating the ice. So here you see a half a meter of ice core. We are 2 kilometers down in the ice sheet and 35,000 years back in time. And each little colored line here is an impurity, so like sodium or ammonium. It doesn't matter really what they represent, but you see many of them have wiggles. And these are actually the annual layers, because many of these impurities have a seasonal cycle. So we use these high-resolution impurity records to date the ice, and we can count the annual layers, and we put a line there. You see every time we are quite certain there is a layer. So here you're looking at 25 years, 35,000 years ago, one by one. And that's what is unique by ice cores, that you really have a good time control of things. And you can say, congratulations, you can see all the years, but what can you use it for? Well, we can, for example, see how fast this abrupt climate change was during the last glacial period. And that's something we really want to understand. And this shows up that temperatures in Greenland were warming 12, 15 degrees in less than 50 years. So that is in Greenland. So that is something unseen of in present day and the entire Holocene. So there are things to learn about the climate system that we can use these records for. There are also other things showing up. This is a recent work. If you measure lead in the ice and you go 2,000 years back in time, you suddenly get this big spike here, this big bump in the lead concentration curve of the ice. And what is that? Well, that was the Romans that had lead mines, and when you melt the lead, you evaporate some of it, it goes into the atmosphere, and some of it falls out in Greenland, and you can measure it. So this is probably some of the first human contamination of the atmosphere that we see here. And the red dots, that's silver, by the way, because they also had silver mining. And these guys here, they actually claim that you can see how well the Romans were doing throughout the period there, and when they had peace and good production, etc. I don't know if that's pushing it a bit, but there's no doubt that this is really this signature of the Romans on the Greenland ice sheet. Another important example is what we see in recent times. And here we see the sulfate concentration of the last 600 years. We see that we have a constant background, that's marine organisms producing a bit of sulfate all the time. On top of them, we have the volcanoes, the lucky eruptions in Bohr. And then towards the last century here, we get this big bump, and that's the industrialization. So with burning of fossil fuels, coal, etc., there's also lots of sulfur going into the air, and that's what gives this big bump. So, doubling or tripling the background level with unseen high values. The curve is dropping off, however, because we have been better of putting filters on the chimneys. It's really annoying to get all this acid rain everywhere. So the sulfate acid is actually being removed now before the smoke is let out. So this is an example of where it has been possible actually to get rid of the problem, at least to some degree. All right. This is maybe the most famous curve from ice cores. We are now going all the way to Antarctica, and that's just because in Antarctica you have much less snowfall, and therefore you can go much further back in time. The annual layers are much thinner, so you can go almost 1 million years back in time. And what is shown here is then the last 400,000 years, and the time is now going from left to right. Sorry, it's going a bit in all directions. And then this is the CO2 concentration of the ice. So you see, for 400,000 years, we have natural levels between 200 and 300 ppm, so parts per million, that's a concentration unit. And we see 4 wiggles here, and that's 4 glaciations. When we have the low values, it has been glaciation, big ice sheets on Earth. And in between, we've had the interglacial periods, the warm periods. And of course, what is quite noticeable here is that at the very end, this is the industrialization, this is us, this is where we are getting out of the scale, now above 400 ppm. And not only getting out, but also doing extremely fast. I mean, there are no natural changes like this whatsoever, probably for many millions of years, but in the ice cores, at least we can see it for the last 1 million years. So that, of course, makes it a little bit hard to predict the future, because we are really making a disturbance of the climate system that is not seen naturally forever, probably. So yeah, we can learn a lot from past climate, but to predict exactly how the result is of this perturbation is still not easy. Yeah, another interesting thing is that you see these warm periods. So that's when we are high up in the natural levels. They are fairly short. So the interglacial periods have lasted typically 10, 15, 20,000 years. And that was a big fear when this curve was seen for the first time in the 70s. This is from the Vostok ice core, the Russian ice core from Antarctica, that exactly we will be running out of interglacial climate and enter a new ice age. Because it looks like, you see from this curve, that they are pretty short and that we could easily end up in a new glaciation within quite a short time. So that was, of course, the alarming news in the 70s and 80s that, looks like we're entering a new glaciation. Of course, that glaciation is now totally cancelled. I mean, there is no way we can get into a glaciation with the global warming going on. Starting a new glaciation means you have to have cold temperatures, snow has to stay over the summer so you can start building up ice sheets. We are right now melting down all the ice on Earth, so there is no way to get into a glaciation. It is cancelled. It's not going to happen for tens of thousands of years. But that was what the fear in just a few decades ago, and it shows about how much we actually have learned about the climate system in this very short time, that we say the exact opposite of what we did just a few decades ago. And of course, this is something that people remember what they learned in school. So when they were told in school that glaciation is coming, and now the scientists are saying that we have a global warming, what is this? This is a big mess, right? So of course, I can understand that viewpoint, but it's just because we have learned so much more about how the climate system works. And this is really an unusual situation we have put ourselves into. All right. So it's unfortunately not only CO2. These are, recent measurements of concentrations of different greenhouse gases, just from atmospheric measurements. CO2 is rising. We have a seasonal cycle. Methane, another very important greenhouse gas, is also rising. It's mostly our food production, rice and cows and things. Environments with no oxygen will produce, bacteria will produce methane. And it's rising. Fortunately, the concentrations are much lower. So CO2 is measured in parts per million, ppm, and methane in parts per billion, so 1,000 times lower concentrations. But still, it's a huge worry because methane is also a very potent greenhouse gas, and it is still rising. N2O, nitrous oxide, is also anthropogenic, so human-produced. We use it as a fertilizer, and the curve has the same direction. The good news maybe is the lower plot there, that's the freons, the CFCs that we used in our fridges until quite recently. And they were banned by the Montreal Protocol 30, 40 years ago, and therefore not being produced anymore, at least not most places. But they have a lifetime in the atmosphere of more than 100 years, so it takes a long time for them to be removed. They are entirely produced by us. They don't exist naturally. And it shows up that they are greenhouse gases that are like 10,000 times stronger than CO2, for example. So it was a good thing to stop the production. It was not therefore it was stopped. It was because of the ozone hole that was formed over Antarctica. But another effect of them is that they are strong greenhouse gases. And they are slowly decreasing in levels. And that's good news. Anyway, all of this leads, of course, to the global warming. We know exactly how greenhouse gases work in the atmosphere. We know that when we have higher concentrations, they trap more heat from Earth and we get a warmer world. So that's exactly what we see in a curve like this, where you see the mean annual temperature measured from the surface of the Earth averaged over the entire Earth from 1880 and then up to today. And there's a very clear trend, especially since 1970, and it's upwards. And every year you will hear in the news or see in the newspaper that, oh, now there was a colder year, probably that's the end of it now, global warming is over. However, there is variability in the climate system and we have ups and downs, and you have to average over some years to get a trend. And I think there's no doubt about which direction this trend is, and it's certainly up. And it is going to continue like this as long as we are emitting greenhouse gases. Still, of course, we would like to know more details about what is actually causing this variability of the climate. And we know a lot about this. I cannot go into all details, but one of them is the volcanoes. They give us cold years, even smaller ones. Other one is the El Nino phenomena that goes on in the Pacific Ocean. This is a phenomena that takes place every 5 to 7 years. And when that happens, you have a very warm surface of the ocean in the Pacific, and that gives rise to a very warm year. So that's the top points there. But in general, it is rising, and there's no doubt about that. Okay, so this is just a figure trying to investigate what is contributing to the global warming. So it's again the same time period we're looking over, and the black curve in the A there, that's still the warming, the global warming temperature that I showed you just before. And then it's just split up into what components are contributing to this warming. That is a bit more than 1 degree over this period. And so it's split into solar components. There's a little variability in the solar output with the sunspots, but you see the contribution is less than 0.1 degree. We have a cooling from volcanoes, that's a blue curve there, and it goes, the small volcanoes we've had recently haven't cooled much, but maybe 0.1 degree or so. Then we have the internal variability of the climate system, the green curve, that's the El Nino, for example. And then we have the greenhouse gases, the anthropogenic component that has led to the major part of the warming there, 1 degree approximately. Right, so what's going to happen when we are warming the world? Well, one simple exercise we can do is to see how much ice do we have on Earth and how much sea level rise could we potentially have. Of course, we're not going to melt all that ice very quickly, but we have started melting it, and the question is how fast is it melting and how much melt will we end up with in the end. And just a simple estimate, we can see how much ice do we have in Greenland, we know it. If we distribute it in the ocean, we would get about 7 meters of sea level rise globally. That's a lot, but Antarctica is almost 10 times bigger. So if we would melt all of Antarctica, we would get almost 60 meters of sea level rise. That's a lot. And then we have all the smaller glaciers in Norway and Sweden, the Alps, the Andes, etc. They are the ones melting first, and they give us rise to the first about 40 centimeters of sea level rise. There's not so much ice stored in those. And of course, we're also melting sea ice in the Arctic, and this doesn't contribute to sea level rise because it's already floating. But of course, it matters a lot if we change the surface color of the Earth from white to dark, as you do when you melt ice and substituted by ocean surface. Right, so there's all kind of measurements going on, of course, about the Greenland ice sheet and the Antarctic ice sheet, and this is just an example of how the mass of Greenland's ice sheet is being measured from year to year. Can be done from satellites. They measure the gravity of the ice sheet, and it's changing because we're melting it. So unfortunately, we do not have these kind of curves for a long period, only since the satellites were up, so the last decades. But the trend is very, very clear. We are certainly melting a lot of ice away from Greenland. And these kind of results are, summarized in these reports that are being made every 4 or 5 years. The IPCC reports, so the Intergovernmental Panel on Climate Change, scientists from all over the world, they compile all the knowledge we have about the ice and about the climate system. And here in 2014 was the 5th assessment report coming, and we just had a new one, an update last year. And that's a huge, this is sort of a Bible in climate change science, that you have all your knowledge there, approved by all the scientists and also by the governments. And this is the status of the Greenland and Antarctic ice sheets shown here in the figure. And red means melting, so ice loss more than accumulation. So for Greenland, you see we have melt, especially at the coast, but actually all over Greenland, we are losing mass these days. For Antarctica, it's not all of Antarctica that is melting. It's mostly West Antarctica, where we have the red part. And it doesn't look so significant in this figure, but unfortunately, it's not to scale. West Antarctica is about the same size as Greenland. So the melt from Antarctica is actually as significant as what we have from Greenland. And this was sort of a bad surprise that has come up the last decades, that it was thought that Antarctica is so far away, it's so remote, it's so cold, you can never change that. That was what I learned in school. But certainly we are melting away ice from Antarctica as well, and this is going to contribute a lot to sea level rise. So that's the lower curve there, just over quite a short period where measurements are good enough. We see the contribution of melt from Greenland and from Antarctica, and then from the rest of the glaciers around the world. And the curves have one direction, it's up, and it's not so scaring. You see the sea level equivalent, and it's in millimeters over this short period. But the trouble is, of course, when we have started this process, it's not going to stop. So we will just have a lot of melt over centuries, coming centuries. Right, and we see all kind of signs. This was the news in the summer that for the first time it was raining at the very top of the Greenland ice sheet, so a little bit south of the camp I showed you. There it was raining, and that's totally unheard of in the summer. Usually you don't have it. So they had a rainbow there that they could observe, which is not normal. Normally it's just snowing. So what is going to happen to our sea level in the future? That's one of the big questions. And here we have a curve that shows past sea level. You see some changes over the last 2,000 years, plus minus 20 centimeters probably. And then we will have some sea level rise in the future. And these reports have been surprised time by, or year after year, that they have always been a bit on the conservative side and underestimating how fast we are actually melting ice. So for each new report coming out, the curve is getting steeper and steeper. So the 2014 report here predicted 40 centimeters of sea level rise in this century, but more recent measurements suggest that this will actually be more. So we have a very steep curve there, and it's not going to stop within 100 years just because the curve does, or the graph does. So, you know, all kind of implications for millions of people living in low-lying sites of the continents. And of course, we have put our cities next to the ocean because it's super convenient that you can go by ship, but it's very inconvenient when the ocean is rising. And it has not been rising for the last thousands of years, not significantly. So it's not something we have experience with, that sea level is not constant. Just to show a more recent figure here, the bad news really is that it's not only rising linearly, it's accelerating. So the very precise measurements we have since satellites were sent up in the 90s, we know exactly the entire ocean surface, and we can see if it is rising or not, and we see that the curve gets steeper and steeper over just a few decades, meaning we have increasing melt and also expansion of the ocean water because it gets warmer. So when you heat up the ocean water itself, it will start expanding, and that's an effect that comes on top of this. But yeah, it's quite certain that this is accelerating because we are simply melting snow and ice faster and faster. So this is really bad news, especially if you live in a flat country like we do here in Denmark. We have a lot of coastline and very low-lying country. So of course, it's also a concern here. And this is just a figure that shows what 5 meters of sea level rise would, what areas would be covered of Denmark, and even 50 meters, that's a dark gray, there's not much left. So we are a rich country here, we can pay a lot and we can do lots of modification and adaptation in the beginning, but at some point you cannot defend a coastline like this. So people are starting to think, yes.
There is one question coming in the chat. Should we?
Yes, please.
At the end, or someone, Aquila is also asking about the melting ice, that it's not only the rise of the sea level, but also the chemicals in the particles. Is that also going to be a problem when the melting ice is going to change what the water consists of? And does that have consequences for life too, or is it mainly that Copenhagen will become a new Atlantis?
Right. So, I mean, sea level rise is one issue, and that's the contribution of the melting ice and the expansion of the water itself. Then, of course, the composition of the water will change, not so much because of chemicals, but because it is fresh water you are melting when you melt the ice sheets. So the salinity, the salt content of the ice, of the water, will be low in the surface, and this is what could affect the Gulf Stream, for example. But the main issue with chemistry is that a lot of CO2 that is emitted into the atmosphere is taken up by the ocean. Actually, more than a third of the emitted CO2 goes into the ocean, and this changes the acidity of the ocean, so the pH value, and this impacts the entire biosphere in the ocean. I mean, all biology is sensitive to changes in acidity and to pH, and we are now changing the acidity of the surface ocean significantly because of all the CO2 that goes in and changes the chemical balance in the ocean. So the acidification of the ocean because of emitted CO2 is another very serious effect that will affect biodiversity and all marine organisms, definitely, yes. So yes, that's another serious issue, definitely. Just getting back here to the sea level rise. I mean, people are starting to get alternative ideas because it looks like we are in serious trouble here and we cannot really avoid this sea level on the long term. So why not do something a little bit more drastic than what we normally think? And here is a Dutch guy, and Holland is also a very low-lying country, and they are used to have build walls against the ocean, and they actually live below the ocean in large part of Holland. So they thought maybe we should take this idea at the next level and build some dikes here, between the UK and France, and another one up here between Scotland and Norway. And then we could have a nice low sea level basin here in the North Sea and the Baltic, and let the sea level rise outside that, and we wouldn't have to take care about sea level rise in all of the big cities we have here next to this area. I'm not advocating for this. I'm not saying it's something that is easy to do, but it is an example of what is called geoengineering. So taking a little bit more serious steps against climate change adaptation, or even for mitigation, that we may have to use some unusual methods and ideas, because we are getting ourselves into this situation where it's really, really unpleasant to get the consequences. Right, so that's just an example. The whole thing, of course, has to do with energy, and we need a lot of energy, and we produce a lot of energy, and the ways we've been doing it are just, you could say, polluting, or at least filling up the atmosphere with all these greenhouse gases that have this warming effect that we know of, and we need to find alternatives. How much trouble are we in? I think this is a good figure to illustrate it. It shows the CO2 emissions over time, so for each year since 1990, and then prediction into the future. And it shows just the 5 biggest emitters on Earth, so the US, EU, India, and China, which has become the biggest emitter of CO2 in recent decades. And then we have the black line on top of it. That is the curve we need to stay below approximately if we should avoid more than 2 degrees global warming, of which we already have the first, And that's a fairly steep curve. I mean, it tells us that we should basically eliminate CO2 emissions and other greenhouse gas emissions by 2050. Otherwise, we are going to get warmer temperatures. And so the figure shows the pledges that the nations, they promised at the Paris Agreement, and since then things have improved a little bit, but cutting down in CO2 is not something that's done easily. And in this figure, already in 2030, the 5 biggest emitters are actually hitting this line, and the rest of the world cannot emit anything. And a few years after, we are all contributing, getting beyond this line. So unless we do something a lot more serious than was suggested just 5 years ago, we're not going to make it, unfortunately. So another way to look at this is to see where do we get our energy from. And worldwide, we can do the accountings and see how much energy do we produce from coal, oil, gas, and then nuclear power, hydropower, and renewables. And living in Denmark or the Western world, you may be a little bit thinking, we just put up some more windmills and solar panels and we can fix it. But stopping global warming means replacing the 3 columns here to the left with something on the right that is not emitting CO2. And certainly the renewable energies are expanding, and rising here exponentially, the green columns there, and that's great. But so are still the fossil fuels, because we are still developing in many countries and we are having a hard time cutting down. The good news is that coal is being reduced now, or at least stabilized slightly, but mostly replaced by gas. That is a better to burn if you have to burn something than coal, because it's polluting less and is more efficient. But you see, gas and oil are basically rising as fast as green energy, and we need to get completely rid of the 3 gas, oil, and coal in just a few decades. And I would say that does not look very easy. You could also discuss nuclear power. Yes, it could be part of the solution, but our experience so far has been that with the existing type of nuclear power we have, it's very expensive to build out safe enough, actually, and it cannot replace completely all the energy production as it is now. Maybe in the long term, but it takes a long time to build up nuclear power. And if you have to develop new technologies, it's not something that is done in a few decades. Hydropower is big dams you put up on the continents, and we have already taken all the good places, and you don't want to flood your entire continent with the big lakes. So there's also a limit to how much that can be. So it is the solar panels and the windmills, for example, that have to replace our power production. And there's a long way to go. This curve is not entirely updated, a few years old, and the renewables are a bit higher now, but it's still very hard to see how this can actually replace everything. So where are we heading? Well, this is, of course, being monitored very closely. And this is an estimate of what will the temperature be at 2100, based on different estimates, pledges and targets. That's what the countries have promised to do. And current policies, that's what we are doing. And if you are on the optimistic side and hope that things are improving, we may get to the third estimate there. But note that we already had more than 1 degree of global warming. We are hoping to stay below 1.5, but the estimates, they are more in the direction of 2-3 degrees, suggesting that, yeah, it's getting very, very hard to reach these, certainly 1.5 and also 2 degrees. There's a little TED video there at the bottom that gives the latest update from Carbon Tracker here that is doing the accounting of the global carbon. I think that I'm sort of speaking my time away here, and this would actually maybe be a good time to stop. I have a few more slides, and I can upload them for you or copy them to you if you want. But that would be a longer story. I would just skip a few now and get to sort of not a conclusion, but this issue that is maybe also something that is of relevance to you, that people get very concerned, of course, about global warming. And every year when we have students coming, learning about all these quite negative things, they come and ask, where's the psychologist? And is one taking care of the climate students especially? It's an issue. I mean, young people are getting very concerned and frustrated. They think, how can I take care of this entire situation myself? And it's not easy to handle it. Of course, it's everybody's problem. It's not only the students, but they notice it more because they learn a lot about it. And there's a few TED videos here also that I suggest them to look at. I mean, it's quite serious, right? It's not only about not eating meat and so on, it's also not having kids and things like that. So people take it very serious, and for good reasons maybe. But it's something we need to handle and to probably take serious that people are very concerned about these issues. Yeah, so I think I will leave it there with just a picture from Greenland here. And
Thank you very much, Anders. That was a very rich and insightful presentation. So yeah, terrific. Thank you so much. You're receiving all the applause, and yeah, having the light sky instead of the depressing prognosis at the end is maybe also yeah, an interesting decision at that moment, because that is a big issue. I also would like to ask about how to deal with it mentally when working in your field. But I also would like to open the discussion to any other questions there might be right now. Do you already have questions? Have we hopefully, yeah. Anything come to mind? Oh, Åsa is raising her hand right away. Please, Åsa.
Sorry, I couldn't find the digital hand, so I thought, but I realized I actually have 2 hands, so why not use them? Okay, thank you very much for a fantastic introduction to this topic. I'm a bit curious to know a little bit about the history of ice drilling, because for me it seems like it requires enormously, it requires a very expensive and shall we call it modern technology in order to save the ice, right, and do all this kind of measurements. So for how long has it been going on? Just a general question about the history of ice drilling and this technologies?
Yeah, so it's something that has been going on for the last 50 years. And it was certainly driven in the beginning by the Cold War. It was entirely driven by the Cold War. First deep ice core in Greenland was drilled up in a place called Camp Century that is up on the ice sheet, and was an American camp where the idea was actually to drill tunnels under the ice sheet and have nuclear missiles in different locations under the ice sheet that could not be hit by foreigners, etc. And also to keep an eye on Russia, from the big radar station that is still up there. So they built this camp for living up on the ice year round under the surface. There was shops and cinema and people living there. And they wanted to drill these, or to build these tunnels under the ice. As we know today, that's not really possible, because you can make a tunnel, but it will be displaced and it will be compressed, and you cannot have railways or anything for transporting nuclear weapons down there. So the whole project was given up. But as part of it, they drilled also an ice core, the first ice core, mostly to learn about the physical properties of the ice, because exactly they didn't know very much about flow or properties of the ice. So they set up this whole very expensive, setup to drill the first ice core. There's an incredible movie made as sort of a commercial for the US Army called The City Under the Ice. I recommend it. It's on YouTube. And there you can see the whole operation. Of course, they don't talk about the main purpose, but they talk about researchers being up on the ice sheet and investigating, etc. And they drilled the first ice core. And this guy, Professor Willy Dansgaard, that I showed in the picture, he was in charge of a mass spectrometer where he could measure this heavy water from normal water, and he didn't have anything to do. And he started taking samples in his backyard, collecting rainwater in his beer bottles, and he took them to work and measured them on the mass spec, his instrument. And he noticed that as fronts were passing over Copenhagen, this isotopic ratio was changing. So he got the idea that maybe from this water composition, you can actually learn something about climate and temperatures. So he got his hands on this first ice core in good collaboration with the American colleagues at the time, and measured the whole thing in very small samples, very detailed, and got this very bumpy curve out that I showed you, that nobody actually believed had anything to do with climate because exactly of all the bumps. But he was very insisting old guy, and so he went back to Greenland, southern Greenland, where there was another big radar station on the ice sheet, took another core and measured it, and it looked just identical to the one from northern Greenland. And that was the point where people realized, okay, it must be the climate. It cannot be the same disturbed ice in northern and southern Greenland. It must be the climate signal we see. And then, expeditions were made to Antarctica and to the best place in Greenland, would think, up on the summit at the top. 2 ice cores were drilled, one by the Americans and one by the Europeans, because now everybody wanted ice cores. And this was done at around 1990. And then, interest about climate has just risen, and so it's possible to get funding. But you're right, it's very few groups worldwide that are specializing in this drilling technique and analysis, and something that has been built up over the last 50 years.
Maybe, thank you very much. That is, can you say that it is kind of a side effect of military interest that it was discovered, that is something
the beginning certainly was. I'm quite sure somebody else would have gotten the same idea as the later point and gone and taken ice cores for anyway, because it's quite obvious with all these annual layers you have on top of each other that this should be a good place to look. But it certainly started like that. And still, we are very much collaborating with the US, not the Army so much, but this National Guard of New York that are flying these airplanes. And we are totally dependent on them. So we really need this collaboration. You cannot transport all that cargo without the airplanes. So we still have the Americans as the most important partner for all the projects going on in Greenland. Mm-hmm. In Antarctica, of course, it's another business. All the big nations, they have stations in Antarctica. It's a geopolitical thing. So you have a Chinese, a Japanese, a Russian, an American, European, Japanese, an Australian deep ice core drilling project going on in Antarctica. It's like sending up satellites. It's something big nations, they can do. Mm-hmm. So there it's not only science, it's also about geopolitical things. But Greenland is so far still Danish, and we have succeeded collaborating with the Americans, and everybody's happy because we get the logistic support, and the Americans can stay in Greenland and do their business there. So yes, I would say it goes hand in hand with the Cold War and whatever political situation we have had. And there are books written about this. I mean, how this has developed, because it's quite a strange relationship, you could say.
Mm-hmm. Very interesting. Are there more questions? Baris is raising his hand.
Yes, thank you also very much from my side for the very interesting presentation. I have a question about carbon capture technologies. So ways to remove carbon dioxide from the atmosphere and store it, for example, underground or somewhere else. Do you think this is feasible, or how are those technologies developed at this point? Because when people talk about those 1.5 or 2 degrees, usually the talk is about that we need to cut emissions, we need to change the way we produce electricity. But I think that some governments are also counting on these technologies, which, as far as I know, are partially not even there yet. So what is the prospect that this is actually going to be possible technically?
Yeah. So indeed, I mean, all these projections for the future that are made by the IPCC models that I brought every year, I mean, all of them that go below 1.5 or 2 degrees warming, they now include this kind of negative emissions, as it's called, so removal of CO2 from the atmosphere. So it's certainly something that the scientists, they count on if they should if we should stay below these temperatures, because we are simply emitting too much and too fast, and we're going to get above at least 1.5, maybe 2 degrees. So it seems like a necessity to remove carbon dioxide also. And how well it will work out, I mean, there has been some investigations and investments also, but I think so far not really to a large scale. And the reason being that it's more expensive to pump the CO2 into the ground than just to emit it. And you're not starting to do that unless everybody agrees that this is how we should do it. Somebody has to pay. So there has been, smaller projects investigating, are there good places to put CO2? Can we do it? What will the cost be? And I think there is success actually. Norway, for example, is doing it. When they're drilling for gas and oil, they actually pump CO2 into the ground because it then releases more oil and gas. So you could say there they have a zero net system. So when it's commercially interesting, it seems to work. And I know for Denmark, it seems to be a very good place actually to put lots of CO2 into the ground, but the government or people are not just starting doing it because you need to pay. So I think there is a big potential. I mean, you're right, it hasn't been investigated enough, but it seems that there is a big potential. My colleagues in geology, they tell us that yes, you can do it, but still it is more expensive, of course. There's no cost on carbon, so when there's no motivation, then you don't do it on a large scale. So I wouldn't give up. I think that's feasible. I think that's part of the solution. Of course, we cannot just emit endlessly because we may have that in the future, but it may actually get the worst of the warming in the end. We have a course now at the university called geoengineering, where the students exactly look into all of these more alternative ideas, and one of them being carbon storage and capture and storage. So it needs to be investigated, all of this, I think.
Mm-hmm. But what would you say from your perspective today as you, what is the most crucial thing that needs to happen to prevent what is exactly, and what can we hope for maybe? What is the best scenario and what is the most urgent thing in your opinion?
Well, different scales, right? There's what we can do personally, there's governmental, national level, and European, and the global. So we have to work on all these levels, I think, and definitely a tax on carbon is the obvious thing, because carbon is a problem, and if you tax it, everybody will have incentive to start cutting down. But it is something that is, best decided at a global level, because then it's even for all. But if it cannot, then you can start in rich countries like Europe and do that, because that will have a regulating effect that is very important. The whole thing is that we have to collaborate on this globally, right? And we do not have too much success with that, honestly. I mean, United Nations is there, and we have human rights, etc. But there's always big fights, and it's not easy. However, I mean, I think these COP meetings, the IPCC meetings we just had in Glasgow, I mean, although things are certainly not going as fast as we would like, I think it is still the way to go. I mean, we still have improvements every time. Certainly not what we hoped for, but this time coal was mentioned in the final statement for the first time, that there is probably a problem with coal. That should have been mentioned 20 years or 50 years ago, of course, but still it is going in the right direction, and more countries are contributing. And the way that things were turned upside down, maybe in Copenhagen or certainly in Paris, that it's not like the United Nations is saying, now we have to do like this. It is on a voluntary basis that each country says how much can we do, and you try to make incentives to make everybody contribute as much as possible. It seems to be a much more feasible way than trying to enforce things, because that's just not working.
Mm-hmm. Thank you. We have 2 hands raised. I think it was Stefan first and then Matze. Mm-hmm. Stefan?
Yeah, thanks so much. And thanks so much for your talk, for, letting us know what you do. I mean, both the more scientific as well as the more experiential part, that was really fascinating. I'm interested in, how is specific to your project, how is media representation a concern? So how, what your findings specifically, where do they go? How do they reach like a wider audience? I mean, I'm so thankful to be here, and for you being here talking to us. But is there strategies? Is there funding for that? Yeah.
Are you frozen, Anders? I'm afraid.
TV crews coming.
Sorry, Anders, you had been frozen. Can you start again, please?
Okay, sorry. You hear me?
Yes.
It's okay?
Yeah.
My internet is unstable. I see that. Sorry. Okay. So I just say that every year we have journalists and then TV crews coming up on the ice sheet in Greenland with us, and there are similar things in Antarctica. There's quite a lot of interest in climate, and the fieldwork is exciting. So it is certainly something that that is part of what we do, outreach. We also have contact with alternative type of outreach, I would say, like artists, for example. And I'm sorry, I should have brought a few slides here, because we actually had ice music playing in the tunnels up on the ice sheet. There's this Norwegian guy, I forgot his name, I'm sorry, but he gave a concert on instruments made by ice on site for all of us. 1 hour concert. We were sitting there in the tunnel freezing like crazy, and with beautiful singing. There's this ice musical festivals, and that of course was also with television and everything, and you can find it online. And I think that's just another way of making awareness, and it's great because we reach an audience that would never have heard of Greenland. Also for children, for school books, it's a good way. And we have artists. We get these beautiful records of what the ice looks like all the way through the ice core, and artists are putting this up in museums, that you see how you go through history as you sink into the ice. And yeah, I think like alternative ways of like combining science and art is actually quite a good way also to making awareness about the issues.
Yeah.
I mean, the best commercial we ever had was when the Queen came, or the Crown Prince, and all the Nordic Crown Princes actually came up, and then the journalists, they just follow in a long row, and you get into these magazines that you would never have a chance of writing into as a scientist. So then you really get a big audience, and probably if the Pope would show up one day, that would be the best outreach we could ever have. And not that I would support his business otherwise, but really it's about convincing people that there's a problem and starting to do something about it. And we can talk to ourselves, and the scientists, they all agree there's a problem, but we really need to make awareness to groups that are not usually interested in oxygen isotopes or whatever. And that's a good way, I think.
Mm-hmm. That's really absolutely. Of course, also the question was energy humanities. What is our role in relation to your findings? But maybe first take Mats's question. Please.
Yes, hello. Thank you, Anders, so much. It's a very powerful talk. Thank you. I would like to ask you a little bit about kind of maybe a little personal question, and then also what you said, or you ended your presentation speaking a little bit about young people's psychology and that kind of things. And then I have personally had a very powerful experience with some marine microbiologists who were talking to me and really opened to me why they have chosen this career. So I would like to ask you, like, how do people get into this sort of science, and how did you start? And for instance, the students that you showed photos of, and I imagine just what it must be like to be a student with you and on these expeditions. And so why do people choose this line of work?
Yeah, so I think it depends a little bit on your age. Because I have to be honest with you that when I started working with these ice cores, it was not really because of a huge interest in climate. I mean, it was in the 90s. We hardly knew about global warming. I was a atomic physicist. I had worked a lot in the lab in dark conditions, and I heard about this opportunity to go out to Greenland and do field work there, and that sounded great. So I was quite adventurous, and that was how I got into it. And then later on, I learned that, oh, we have some issues here. There's some global warming going on, and we can actually learn about this from the ice cores. So I think young people today, I mean, they have quite a different view because they are aware of the situation. And I would say my most important job now is, of course, doing the science and the ice core drilling, but actually to be head of this climate change program, where we have 100 students coming every year learning about climate change and going out and getting jobs and making a difference. So I think it's crucial. And I mean, I know it's starting in public school now, and the students, the pupils, they learn a lot about these issues, and they're really interested in it, and there's a lot of interest from young people to study climate, and some of them will end up with us going to Greenland, of course. So it's very different. I mean, when I started as a glaciologist, the main interest was to learn about the ice, the physical properties. That was why we had the ice course. And then we just realized that there was, we can use it for something else. So it has changed a lot over the last decades, and I see a lot of enthusiasm among young people. I must say, I'm really impressed. So I'm quite hopeful in that respect that there's a lot of motivation.
Yeah, that's also interesting regarding the aspect of depression, because in my research on climate activists, it's also a huge topic, and that they suffered from depression, and then they looking for a way to go into action to overcome that feeling of despair and depression. So that would be a typical career of your students too, of a lot of them.
Yeah, they want to make a difference, definitely. And I always tell them at the first lecture that you guys have the opportunity to make a difference. I mean, you can learn about this topic, you can get jobs, and you can make a difference. Contrary to most people, right? I mean, most people don't have a clue, and also they can't do anything about it. So really, we have an opportunity here to be rich and well-educated and having influence. And so, of course, you can get a depression. It doesn't help anyone. So try to take the positive view and use your will and your energy to make a difference. And that's what most of them do.
Jenny asked a question in the chat, but I'm wondering if Mimi's question is maybe directly relating to what we are discussing. Then I would take your question later, Jenny. Is that okay?
That's fine.
Yeah. What are you? Hello, Mimi. What are you asking?
Hello. I just thank you so much for the talk. First of all, it was really interesting. Just in the last part, you mentioned this, that you went into the whole field because of the eyes and because of the very concrete work of working with the eyes. And I was just, during your talk, I found it just hit me really hard, the fact that the picture with the woman just standing with the ice and cutting it up, and that very concrete work, and then the whole issue of the global warming, how far there is from the concrete work of working with the ice, and then this whole philosophical humanities problem of how to deal with global warming. And then you mentioning that these new young students have the possibility of actually doing something about the problem. I just thought about this this part of the, like, what role does this play in the education of the students, of the dissemination of the information, as opposed to just the actual learning about the properties of ice and the very concrete stuff that's very difficult for me to kind of connect with, because that's totally not my field. But like, how do they learn about how to talk about it, how to get the information out and stuff, because it's so far from the actual physics or properties, or maybe it doesn't.
No, I see your point. I mean, there are different kinds of students, right? And some are good at being specialists into very technical issues, working with complicated physics and analysis, and they're good at that. They should do that. Some are good at more social sciences things, and talk to people and do things like that. And we need everybody. And you can specialize in what you're good at, and knowing that it contributes to either understanding climate or doing a mitigation, adaptation, whatever. And I think there's a need for all good, well-educated people. So the climate change program we have in Copenhagen is like 50% natural science and 50% social sciences. So we are fully aware that it's not natural sciences that are going to solve the issue. I mean, it's a social thing. It's a political thing, economical thing to make change. But it's a sort of mixture. You need to have a background, know what is the issue, what can we do about it, and then you can either specialize in this natural science part, like where I am, or you can go into politics or whatever, more social sciences. And we try to make the education broad, that the students have an idea about both fields, because it is connected. And that's one of the big challenges, that we actually used to be in our little physics tower over here, and certainly not talk to the social sciences, because they are a little bit weird. And the same goes the other way, I think. And we have very little exchange, even within our own university, among the different faculties. And that's a bit of a shame, because we actually need to strengthen that. I mean, we need to understand social science in order to make a difference and change here, and we need to use natural science to understand the problem and make solutions. And it goes hand in hand, and it's ethical issues, it's psychological issues, and everything. So we try to teach the students a little bit of everything in the first year, and then they will typically specialize, and some will do interdisciplinary master thesis, etc.
But you don't have any philosophical or more humanities-oriented aspects in there, do you?
We have ethics of climate change. I guess that's the closest we get.
Yeah. Okay.
I mean, it is. It is. In the end, it's an ethical question, right? Because if you have a 5 years horizon, you don't care about climate change, because the main problems are long term, and so it's for the next generations. And our economy is probably not really tuned to take care of next generations. So you need to have that view of it, definitely.
Mm-hmm. And is also, for example, colonialism a topic in some way, or where would that be addressed? And I'm also wondering, if I may just elaborate quickly, you are mentioning how you're collaborating with the US and you are relying on them. I'm also wondering, are you having contact in some way with the Greenlandic people? And what is they for example are also very concerned, of course. Mm-hmm.
Sure. Okay, so that's many questions. I mean, first of all, I only spoke about the collaboration with the Americans, but actually it's an international effort. I mean, we have Russians, Chinese, Japanese, Koreans, all European countries, South Americans, Indians collaborating in these projects. So that's a big international community. Then concerning Greenland, we certainly welcome every possible contribution from Greenland, but there is a problem that there is no education in natural science at university level in Greenland. So it is actually very hard to find qualified students. We have some that come to Copenhagen or other universities from time to time, and we have a professor that is Greenlander, and certainly we are happy to work, and we want to be involved. But I must say that we have had very little contribution from directly from Greenlanders, simply because there's I think a lack of education in Greenland. I know that they are trying to build up a bachelor in natural science, and the fishery is the main issue in Greenland. So that's and mining maybe, but so far there has simply not been enough will or students, I would say. Yeah, so it's not because I mean we are not interested, but it's just very difficult.
Yeah, well, that's really a big topic. I think that would burst the whole discussion for the next hours. Because it also addresses, of course, the historical development of education in Greenland. And but yeah, I just had in mind about the encounter, for example, the important fifth Thule expedition with Knut Rasmussen, where he was really relying so much on indigenous people. And I was wondering if that in anyhow, or the knowledge of indigenous people, if you ever encounter something in your work that makes you question something we are doing from our technological approach, or is that really off the topic? And
well, it's not my personal research area, but certainly, I mean, there are people looking into what is known by ancient people or people who have lived with nature for a long time, and how do they see nature, and what experience do they have with climate change. And I mean, there are lots of people working with Greenlanders along the coast and trying to learn from them. And I think that's a super good approach. I mean, it's just that the very concrete thing we have to do on the ice sheet is a very technical thing, and you need skilled manpower, and that has to be highest priority. And for example, we have lots of Icelanders coming because they are just driving around on their glaciers up on Iceland and have lots of experience with tourists and how to survive in the cold. I think that also in Greenland there has not been a tradition of working really on the ice. Actually, you try to avoid it, I think. Traditionally, so it's not. I mean, sea ice is the area of the Greenlanders, right? But that's a very different ball game from the ice sheet, and it has not been possible to go up on the ice sheet. You know, you really can't do that, and there's no reason to go there unless you have very specific tasks. So it's not something that has been done traditionally. I mean, people lived at the coast from fishing and not going up on the ice sheet. So it's not like we can pull on I think history there, because there's no link.
Yeah, I see. Well, I have to apologize to everyone that I crashed a little bit the discussion with my questions. I hope that's okay. It was just something I saw that fits now, but eventually, Jenny, please.
No, it's totally fine. I was actually going to say that Aldo wrote a really interesting comment. I think we should skip mine because I think his is like a good natural segue. And it's really interesting what he just wrote. So maybe either he could read it or Anders could read it.
Yeah. Do you want to read it, Aldo, or should Jenny read it?
Yeah, please, Jenny.
Oh God. Okay. Where is it now? I got to look at the chat. Okay. I just want to share a quote for reflection. Is this from Time, like a report from, what is Time report? Is
yeah,
that
like news.
Yeah, the news. Okay. The cause of global warming are human. Time report. The causes of global warming are human activities, but they are not. The Maasai who were and are being displaced have nothing to do with global warming. It's all of us, the Western and mimetically Westernized middle classes, after we fell into the trap of modeling ourselves on the mimetic model of the Western bourgeoisie, liberal, mono-humanist man too. I guess that's from Sylvia Winter on being human as praxis. So yeah, I thought that was just interesting. What that quote is basically saying is that that's like, if we look at the climate warming as the actual source of the issue, that's a fallacy, that we have to look deeper. Is that what you're trying to point attention to?
Yes, I just wanted to share it, and so it was not a question because I think this was more like sociological stuff. But I was just thinking this that we cannot say that everybody are guilty about the global warming.
Oh no.
But also when we say, for example, India per capita won't be as pollution. Also, each person produces less pollution than each person from America, for example.
Sure.
So just that, but I didn't want to introduce this kind of discussion because I think that this is more physicist discussion. So that's the reason I just wanted to share.
Yeah. No, but it's definitely an issue. I mean, for history, we know who made the pollution in the beginning, and there are countries that have not contributed very much because of development, that there has not been the same development, and so the pollution has not been that strong. The problem is, of course, that we will be 9 billion people in the future, and if we live like we do in the Western world today, all of us, it's going to be a disaster. We can't do it. So we need to have different ways of living for everybody in the future. And I mean, we just saw China made the same industrial revolution as the Western world did 100 years before, right? And is now the biggest emitter of CO2. And this should hopefully not happen for India and other countries that are now rising their standard of living, because that will be a total disaster. So we need to have alternative ways of producing energy for everyone. Otherwise, it's going to be a disaster. And of course, at the IPCC, this is a big issue. I mean, the nations are fighting each other, right? Because historical reasons are I mean, also part of it, who made the disaster. But I think potentially we can all contribute to a huge disaster in the future if we don't change our way of living. So it's something that concerns all of us.
But also maybe especially the question how the West gets away from its addiction to fossil fuel.
Yeah, absolutely. I mean, is it 5% of the world population that is flying, or is it 10%? I mean, it's us. And there's no doubt who has burned the most fossil fuels. But that's also why, of course, the Western world should contribute as much as possible to find solutions and try to mitigate as much as possible. But in the end, we will all have to have a different way of living than the Western world had the last century, because it's not a way forward.
Yeah. Aquila?
Yeah, hi, sorry, I was putting some kind of emojis, I don't know. No, I think I also just wanted to comment on that. Like, I think, yeah, in a way, I think the problem is that we are also trying to go the linear Western way, right? Kind of thinking that that's the only way forward, is the way it was done in the previously with the Industrial Revolution and everything. And I guess it's a matter of also changing and not trying to look at the Western way as the only way that it was done correctly, because it wasn't, kind of.
Yeah, I mean, we can say that, but there's also, I mean, if you look at much of Asia, when people start getting richer, they eat more, they travel more, they do the same things as the Western world has been doing, because everybody wants to have a good life and everybody wants to see the world. And that's not strange, but it's just not possible, unfortunately, to be polluting as much as we have been doing so far. So I think we have very few decades here to do something serious, right? And to change people's mindset completely, saying, no, you're not interested in having a good meal, you shouldn't travel because it's not good. That's going to be very, very hard to convince people, especially because when you have the possibility, you will do it. Like we did. and like we've been doing. So I think we have to find a little bit of less polluting ways of doing some of the things that we have been doing, because there's a very strong wish to do many of those things. And there are ways. I mean, we should not eat beef as we have been doing, but maybe we can make meat in a different way, or make things taste like meat so you have the same experience. And we should not pollute when we fly around. We have to have alternative fuels and stuff. I mean, we are not going to close down airports and not let airplanes fly. I mean, I think India just bought the 200 Airbuses here the recent years, right? And of course, because it's practical and you want to travel. And all this investment is not going to close down because of global warming. I mean, it's so costly to invest in all this transport. And so we need to have alternatives that we are not polluting as much when we use it. I mean, there are people who want also to make a revolution at the same time, saying the economy we have is not working, we have to change that also. I think that's not possible in 20 years globally. I think you can change the economy. You can put a tax on carbon so that the economy helps to regulate the way we need it. But to say that we should like turn back time or live a more primitive way, I mean, we can do it to some degree, but globally, you're not going to convince people about that. We can be a few intellectuals here at university who say, okay, we will stop travel, or stop polluting and live with very healthy and everything. But globally, you're not going to convince people about that. I don't think so. What should the argument be? I mean, people want to do what they can, and when they can afford it, when they can pay for it, they will do it. And so you're not going to convince people. We need to convince everybody that we have to do something about climate change, but we can't do it by saying people cannot do this or that. We need to make incitaments. We need to make taxes and regulations that will make people do things in a way that is not so as it is now. That's my view. Time scale is very short. If we had 200 years, we could make a good plan for what we will do in 200 years from now. But we have 20 years, and that's a very short time. And we have an economy that works. We just need to change it, regulate it so that it works our way instead of as it is now. That's how I see it.
But that means also that you see a strong role of technology, or how would you?
It's part of it. Yeah,
but it's
definitely.
It's not the primary force that you would say the solution of humanity from its crisis they got into with technology is technology.
I mean, to produce energy in as much as we do now, and even larger amounts as we will need with a larger population, it has to be a technological development. And I think it's perfectly feasible. I mean, look at what has happened the last 100 years and how things are changing, how fast they're changing. I think we're too slow. I think we cannot reach the 1.5 degrees goal without having negative emissions or doing something more. But I think technology will basically provide us with the green energy in a little bit too late.
Well, I think that is, of course, also a very good end. But if I just may ask quickly one last question of personal interest, of course, because you have been witnessing the development of global warming and from the 1990s and trying to raise awareness as a scientist. But the examples that you mentioned, also bringing media up there, how do you regard the role of the global climate movement in the context of raising awareness? Do they think do you think that the youth movement of the last 5 years was different than before other movements?
Absolutely. Yes. I mean, we haven't had anything like that. We had environmental concerns, right? When I was young, it was the environment, but this is what we see now with climate change. I mean, it's completely different scale. And that's actually what makes me quite optimistic. It is that you really hear from the younger generation, we want something else on the table now. It's not going to work like that. And you see it has a huge impact. I mean, in the end, we are blaming all the time the politicians that they are not doing things that we want them to do. However, the politicians will do exactly what we tell them to do if we all tell them to do it. I mean, the main problem, you see it in Denmark, for example. We had now for the first time an election that was actually where climate change was very important, because now the majority of the population is aware there's an issue. They were not before, so then they were more concerned with other things. But if you have really a global movement, which I think we have now, starting with the youth, you will also change the politicians and you will make them do what is necessary. It's not going fast enough. That's the main problem. We are too slow, and it's too difficult when it has to happen globally. But it's definitely moving in the right direction, and I'm optimistic. Not that we will hit the goal that we want, but that we can then get a little bit worse and then fix it in various ways, using all our knowledge and innovation. Yeah.
And maybe also imagination, where the humanities might come in again in the end.
Absolutely.
With science fiction and climate fiction and things like that.
We have to be a little bit careful, because history tells us that this geoengineering thing, you can also do things that give unexpected results, right? I mean, the CFCs were genius for the fridge, but they then had some side effects, and an ozone hole and things like that. And we see that over and over with the smart chemistry and things like that, that we think we're fixing a problem, and then there were some side effects that we didn't want 20 years later. So of course it's not easy. So I would say we should play it as safe as possible. Solar panels, windmills, I mean, they are not making any damage. They may be ugly to look at, but they don't have a 10,000 years issue following them or whatever. So let's use that as much as possible, and then do some extra things if necessary.
The greatest source of energy of all, the sun. So let's try to work with it.
Absolutely. I mean, we used steam, and then we used electricity, and then diesel. Why not change? I think it's feasible. Absolutely.
Great. Thank you very much for this positive last notes.
We need a positive end, right?
Well, we need a positive end somehow.